Good morning, children. Let us start the class. Today, the continuous portion of the lesson 1, electrostatics. Unit 1, electrostatics. Today we can continue. First 3 classes we have learned about the electric field, the electric charges and the electric field lines and all. Am I correct? Have you learned that well? Derivations, yesterday's derivation, that equatorial line, that last class derivation, the electric field, the equatorial line, axial line. That question is very important. That also you write and see several times and learn well. Okay. So today, what I am going to take now, the torque experienced by an electric dipole in the electric field. Torque experienced by the electric dipole. So, torque experienced by the electric dipole in the electric field. Yesterday, we have learned what is electric dipole. What is electric dipole? Two equal and opposite charges separated by a small distance constitute electric dipole. Am I correct? Say along with me. Say, two equal and opposite charges separated by a small distance constitute electric dipole. For example, some permanent dipoles, some molecules we can see carbon monoxide, CO, water, ammonia, then hydrochloric acid, this like this. Some examples we have learned, isn't it? So today we are going to learn this electric dipole. Okay, torque experienced by an electric dipole in the electric field. Okay, now we are going to consider an electric dipole with the dipole moment P vector. This dipole have the dipole moment P vector. We want to place this electric dipole in a uniform magnetic field. Okay, I am drawing the diagram. Okay, what is uniform? Here we have to take two electric charges. One have plus Q, minus Q, another one plus Q. Midpoint is O. Okay, equal distance. From the midpoint, the first charge minus Q and the second charge plus Q, both are at same distance from the midpoint. Okay, this is an electric dipole. This one kept in the uniform electric field. Okay, so in this field, what is uniform electric field? They equally spaced. The electric field lines are equally spaced and they are in same direction also. You see, for showing the direction, I drawn arrow marks. So they are equally spaced in and they are directed in same direction. Okay. So if two charges have equal values and they are separated by a small distance, that we can say as electric dipole. Here this plus Q and minus Q constitute an electric dipole. Okay, from the from midpoint O, it is equally spaced. So now the total torque we have to find out. So you see here two points are there. This is plus Q, this one minus Q. This minus Q experiencing a force, that is minus QE vector. This minus QE vector. Okay, this is acting towards in this direction. Minus QE vector, this minus Q. Here this plus Q charge experiencing another force. Okay, that is plus QE. This one acting towards this side. So plus QE vector. Okay, these two electric charges are experiencing some electric, some force. Okay, some electric field is there, some force is there. Okay, first charge is minus Q, second charge is plus Q. Okay, so here these two forces are different. So because of that, they are experiencing different forces. They are constituting a couple. Because of that couple, a torque is forming. Okay, the dipole, electric dipole is experiencing a torque. Okay, so the total torque, the total torque of on the dipole. The total torque on the dipole about the point A. Point O. So torque we can write as tau vector. Okay, this tau vector. Here, one more thing you see. This minus Q we can take as A. This plus Q we can take as B. Okay. So here and we want to find the resultant, so want to draw that here. This is the diagram. So here tau is equal to OA vector into QE vector. Okay, OA, the total torque of the electric dipole. Okay, plus OB vector into QE vector. Okay, here this is minus value. This QE is minus, so minus QE. Here plus QE. This is the total torque. The total torque on the dipole, electric dipole about this point O. So the magnitude of the total torque we have to find out now. The magnitude of the total torque. So here we are using the right hand screw rule. Here we are using the right hand screw rule. It is found that torque is perpendicular to this plane of the paper and directed into it. The torque is perpendicular to this plane of the paper and directed into this paper. Okay. So that the direction of the torque is inside. So it is the torque is perpendicular to this plane of the paper. Okay. So this the magnitude of the torque we have to find out. So the magnitude of the total torque. We also write here cross product. So OA vector minus QE sin theta. Okay. So this one we want to write inside modulus. So plus OB vector plus QE plus QE modulus QE sin theta. Okay. So OB, OA value we know A. So minus Q AE sin theta plus Q, this here A. So QAE sin theta. OB and OA. So here we can take the common terms outside. So we will get here AA. So minus so tau is equal to, if we are taking this inside the modulus, the minus will go. So A QE sin theta or QA E sin theta plus QA E sin theta. Okay, so we can write QE into A plus A, 2A. So A is 2A together, A plus A, 2A sin theta. Okay, this only the final equation, final formula for this term. Term is equal to QE 2A sin theta. Okay. Now, we know 2AQ. 2AQ. Tau is equal to, we can write tau is equal to Q cross E. Q cross E means what? No, Q cross E not. E 2AQ sin theta. Okay. 2AQ. P vector equal to 2AQ. You know. So tau is equal to E P vector E sin theta. So we can write tau is equal to P cross E. P vector cross E vector. Okay, this is the formula. So when the theta, this theta angle is in between, the angle between the dipole moment and the electric field. Okay, so P and the angle between P and E, that only the angle theta. Okay, so if theta is 0, the value is maximum. The torque is maximum. When the theta is 0, the value is maximum. Understood now? Now the magnitude, we can read that electric field is not uniform. What will happen? If the electric field is not uniform, the force experienced by plus Q and the force experienced by minus Q will be different. If they are different, net torque will be arise there, net force also will be arise there. If the uniform, the electric field is not uniform, the torque is also, net torque is also there, 0. That net force is also there. Okay, so there will be some net force and net torque is there. Sorry, that electric field lines are not uniform. The torque, net torque is there, net force also there. That is the thing here. If that is uniform, that answer is the torque is equal to P cross E, P vector cross E vector. Okay, once more. The torque experienced by an electric dipole in the electric field, here plus Q, minus Q, plus Q2 charges are there. They are equal and separated by a small distance and constituting electric dipole. So first minus Q experiencing minus QE, next second plus Q experiencing plus QE force. Okay, so both are experiencing some forces. That forces are also opposite. So the total, it is producing a torque. The total different forces, different direction. So it is producing torque. So that torque, the total torque on the dipole, tau is equal to, tau vector is equal to O vector cross minus QE vector plus OB vector and QE vector. Okay, cross QE vector. So these two are cross products. So OA, if we are writing sin theta, we have to OA vector modulus QE vector modulus and sin theta plus, then this also we have to write sin theta. So we know vector product. So top is equal to QAE, OA value A. So QAE sin theta plus QAE. So we have to write 2AE sin theta. 2AE, both we have adding 10, 2AE sin theta. So QE 2A sin theta. So here tau vector is equal to, then after finish this we have to come here. Tau vector is equal to E vector. So 2AQ sin theta. What is 2AQ? 2AQ we know electric dipole moment for this electric dipole. Okay. So tau is equal to PE sin theta. P, this one P. P is sin theta. P cross E. Okay. So P cross E sin P sin theta. So we have to write tau is equal to P cross E. P sin theta value P cross E. P vector cross E vector. Well, if you understood now. Now in the next we have to learn that electrostatic potential and potential energy we have to learn. Electrostatic potential and potential energy we are going to learn here. Okay. So here what is potential? In mechanics we know potential energy is the conservative force. Potential energy is the conservative force. Like that, gravitational force is also conservative force. In the 11th standard we have learned conservative forces and non-conservative forces. Conservative forces. The conservative forces independent of the path and depends on the initial and final positions. Okay, but non-conservative forces depending on the path only, but not depending on the initial and final positions of the charges. Okay, so here this potential energy is the conservative force. Like that, gravitational force also conservative force. Okay, so gravitational, what is this gravitational potential energy? Have learned in the 11th standard. Okay, so this here in the earlier lessons we have learned Coulomb's force. This Coulomb's force is inverse square law. Okay, inverse square law force. This Coulomb force obeying inverse square law. So this force is called as inverse square law force. Okay, so this inverse square law force, this force also a conservative force. This inverse square law force also a conservative force. Okay, so we can define this potential energy for the charge configurations. For the charge configurations we can use define this potential energy. Okay, so here electrostatic potential energy and electrostatic potential energy and the electrostatic potential energy. Okay, in this electrostatic potential and this electrostatic potential energy, we have to consider a point charge, positive charge Q. Okay, this is a positive charge Q. Now we have to this one we have to fix it in the origin, where the first charge Q is there, that is the point center. Okay, the main point. So in this another point we have to take, that is R. That charge also positive charge only, another positive charge. we have to fix. Okay. So here this charge are both the charges are positive charges. These charges, we know two charges are there. Both are same polarity. They have some repulsive force. Okay, but we have to bring this plus Q charge to another point P. Okay, so to bring this plus Q charge to P, from R to P, we have to do some work against this repulsive force. We know already, if both are positive charges, they have some repulsive force. So to overcome this repulsive force, we have to do some work. Okay, work. We have to do some work. Okay, so work is there. So while doing this work, you see that Q, this charge plus Q, that both the charges, this is source charge, this is the this is the source charge, this is the test charge. Okay, so both the charges are there, so one Coulomb force is acting there. Here some external force we need to overcome this repulsive force, then only we can do some work. So the test charge Q dash, this charge we can take as plus Q naught Q dash. So this one Q, both are same charges, but this one Q, this one Q dash. Okay, we have to bring this from R to P. Okay, so this F external, this here some Coulomb forces there in between this. So F vector this is Q dash, capital R, here we have to bring P. Okay, so F external, how much external force, if we are bringing this, how much external force we need to overcome this Coulomb force, that is equal to F Coulomb force. Both are totally equal, they are both are equal and opposite. Equal and opposite. So the work done, we know we need to find out the work done. P from R to P, how much work done we need to vector external dot dr. Okay, dr is the distance. So R is the distance. So we have to bring. So while bringing this, we have to bring with constant velocity. So F external. So F external value we know. What is the value of F? F value is equal to, according to Coulomb force, minus QE vector. Okay. So minus QE. So this one Q is, that is Q dash. So this is potential energy. Okay, for this. At the point R, the potential energy is UR. At point P, the potential energy UP. So the difference in potential energy is del U. Okay, this is work done. So del U is equal to W. Okay, so what is that? Equal to integral P to R F external dot dr vector. Okay, dot dr vector. Since these two are equal, these two forces are equal, that is equal to minus Q dash E vector. Okay, according to Coulomb's law. Okay, so del U is equal to, we have to find out del U. Del U, we have to substitute this value here. So how will you substitute? P R to P, integral R to P, F minus Q dash E vector dot dr. Okay, so dr also vector, dr vector. Now the potential energy difference So here the potential energy difference is UR minus UP or del U. Del U is this, the potential energy difference. We can write the potential energy difference per unit charge. Okay. We have understood these steps. Yes, so thank you. Potential energy difference per unit charge. Potential energy difference per unit charge taking time. Del U divided by Q dash. Unit charge is Q dash, the test charge. So Q dash then equal to Q dash integral R to P minus E vector dot dr vector. Okay, divided by Q dash. This Q dash cancel. So del U divided by Q dash equal to integral R to P minus E dot, this minus we can bring outside. So E vector dot dr vector. Okay. So this equation is called electrostatic difference between P and R. Electrostatic difference between P and R. This is called as, this equation only, electrostatic difference between, potential difference between P and R. Electrostatic potential difference. Simply if we are saying electrostatic potential difference. So we can write potential means what? Vp. V is the symbol for Vp minus Vr equal to del V. Okay, that's also the same thing only, minus E vector dot dr vector. Okay, so we can write this del U is equal to, what is del U? Del U is equal to Q dash del V. Okay, this totally we can say del V. So del U is equal to, del U, only del U writing time, del U is equal to Q dash into del V. Okay, this is the formula for the electrical potential difference. Okay, what is electric potential? We want to know the definition of electric potential. The electric potential at a point P is equal to the work done by an external force to bring the unit charge from infinity to the particular point, okay, in the region of the electric field. Okay, that is electric potential. What this electric potential, the unit of this electric potential is joule per coulomb. The unit of this electric potential is joule per coulomb. This one we can, in the practical unit, volt. Okay, the practical, this name is by the name of the inventor of the battery, Alexandro Volta. Volt is the practical unit of this electric potential. Okay, so this what is electric potential? Once more, the electric potential at a point P is defined as it is equal to the work done by the unit external force to bring a unit positive charge from infinity to the particular point in a region of the external field. Okay, so the formula for this is Vp is equal to minus integral from infinity to the point P we are bringing. So E dot dr vector. Okay, this is the formula. Okay, the potential energy difference per unit charge. So first, this potential we are bringing this. I am writing here. Electric potential. Okay, what is electric potential? The electric potential at a point is defined as which is equal to the work done by the external force. to bring the unit charge from infinity to the point P in the region of external electric field E. So the value is Pp is equal to minus P integral minus from infinity to the point P E dot dr is the vector quantity. Okay, this is the value. Next, electric potential due to point charge. So that one another day we can take. Once more we can revise this. So what is electric? Here in this electrostatic potential and the electrostatic potential energy. Okay, electrostatic potential, what is that? This potential energy, W is the potential energy, electrostatic potential is Vp. Okay, so here W by Q dash, we have to take outside P2R minus V dot dr. So del V is the change in Vp minus, so I have written here, that one not. So here del V. Okay, so here del V is del U by Q dash. Okay, so potential energy, change in difference in potential energy per unit charge. So that is called electric potential difference. So that electric potential is del V. Okay, so here what is that electric potential? The definition is very important. Okay, so here in this definition you see some important points are there. Okay, the important points, the electric potential at a point, P depends only on the electric field, which is the source charge, source of potential only, source charge only. Okay, source charge, electric field. So the source charge has some electric field lines around it. The source charge has some electric field lines around it. So the electric potential depends only on the electric field of the source charge, not on the test charge Q dash. That is the first point. Okay, if a positive charge is bringing from infinity to the particular point at a constant velocity, because the external agency should not impart any kinetic energy to the test charge. So that we cannot see any kinetic energy to the test charge. Okay, so that is the first point. What is the first point? Electric potential P. The electric potential P depends only on the source charge Q. It is not depending on the test charge Q dash. Okay, so next, second is the unit of this electric potential is joule per coulomb. Joule per coulomb. Okay, joule per coulomb. The practical unit of this electric potential is volt. This volt is because of the name named after the inventor of first battery, Alexander Volta. Okay, so Alexander Volta. Alexander. The Alessandro Volta. Okay, according to this his name, they named this practical unit. Okay, so in the next point we can say the potential difference between two points is expressed in terms of voltage. So 2 points, the electric field difference between the 2 points we can write as voltage. The potential difference is otherwise called as voltage also. Okay, so once more we can see this del U, that is the difference between the two potential energies. Del V is the potential difference between two electric charges. Okay. So children, today what we have learned first? First we have learned about this torque experienced by an electric dipole. Okay. So torque, what is torque experienced by an electric dipole? It is torque experienced by an electric dipole. That electric dipole is in a uniform electric field. Okay. The electric that is in a uniform electric field. So if it is in a uniform electric field, it is the two charges are experiencing different forces, but it is equal magnitude, but that polarity, that opposite charge. Okay. So this is here plus here minus q, this one plus q. Midpoint is O. So the distance between here A. So equal distance. So it is separated by a small distance and equal charges. So they two are experiencing some force. So minus QE vector. Then here plus QE vector. Okay, both are acting at different points. That forces are acting at different points. Because of acting at different points, the dipole is forming. No, a torque is forming. Why torque is forming? Coupled, equal and opposite forces. Okay, they are producing a coupled. So these two forces. So a torque is there. Because of the torque only acting on this, the total torque. We are going to find out the total torque acting here. Okay, so that total torque, the torque is the formula for torque, the notation. So symbol for torque is tau. So this one we have taken A, that one B. So OA QE plus OB QE. Okay, so that looking time, that OAOB, so we got the answer at last. Tau is equal to P vector cross E vector we got. Okay, so tau is equal to, that is if they are that angle, the angle between the two theta is, if the theta is 90 degree, the value of torque is maximum. Okay, the value of torque is maximum when theta is 90 degree. This one we are using the Torque's rule. Okay, the magnitude of the torque is equal to P sin theta. The torque tends to rotate the dipole and align it with the electric field E. So once P vector is aligned with E, the total torque of the dipole becoming 0. Okay, the dipole becoming 0. If the electric field is not uniform, then the force experienced by the force experienced plus Q is different from the value that force experienced by minus Q. Okay, in addition to the torque, there is net force also acting there. Net force also acting there, net torque also acting there. When we are, you see that not uniform field, we can denote like this. The fields are not uniform. Okay. The field is uniform. They are equally spaced in between all the electric field lines. They are equally spaced, and the direction also same direction. This one uniform electric field, non-uniform electric field is like this, but same charges. Separated by a small distance. This constituting electric dipole. Okay. So children, we have learned today about this electric torque acting on the electric dipole, because of this electric dipole, then this electric potential energy and electric potential we have learned. You learn well this derivation, two derivations. These are important questions. So in the note you write and see several times and learn well. Okay. So thank you.